Okay, students, let's begin lecture. Sorry, sorry it took so long to get rolling. We're going to do some clicker questions. We got a bunch of them. Get your clicker ready. And we're going to try to finish up. We're going to try to finish up thermal concepts today. I have some comments on the French fry problem, where you have to burn off a certain number of calories by doing stadiums. That's why I was taking a little extra minute to get started. And then we'll finish, and then we'll go back and do some more melting and heating of ice. And I'll give you a kind of a general strategy, then we'll try it on iClicker. And so let's take a look at the problem of doing stadiums. Let's swap over to laptop. Okay, so here's the problem of doing stadiums. And I just remember all this from office hours. We had office hours yesterday, and we did together a nice instance of this particular problem. Given a student that eats 375 food calories of French fries, the mass of the athlete being 72 kilograms, the height of the stadium stairs at the top 12 meters from the bottom, and figuring that you're doing mg delta y of work, Gabby, to get up there. So the force that you have to exert to get up, move vertically anyways, is mg. All right? And then the distance vertically that you move is delta y 12 meters. And Jason, if you work all that out, it works out to 8467.2 joules. Okay, that's the same number each time. And it is neglecting the fact that you're actually using a little bit more than that, because actually walking up the stairs, you go vertically and you go horizontally. Now, we're not counting the horizontal. We're assuming that it's pretty easy to move horizontal. It does take a little bit of muscle power, as you know, to move horizontally, a few joules for each step, but we're going to neglect that. Most of the joules are going to be in the actual vertical task. Also, we're ignoring or neglecting the number of joules it takes to walk back down. All right, now that is also another fairly easy thing. You can't do it by just kind of blobbing and rolling or oozing down the steps and not exerting any work. You know, it does require a little bit of muscle power. But we're assuming again that the major part of the joules is going to be in the vertical work. So 8467.2. Now, what you have to do in item number 4 here is convert that to a certain number of calories. So every joule is 4.184 calories. All right? So 8467 times 4.184, that's going to be 30,000 something calories. All right? And then each of those calories, for every 1,000 of those calories, you have 1 food calorie. All right? And so you again, so now you divide by 1,000, and that'll tell you how many food calories you burn up going to the top of the steps. Now, as I recall this one, is this correct? 185 trips to the top. Okay. And how many, Amber, how many calories was it? How many regulars? Oh, we worked it the other way. Yeah. The other way to do this, which we did in office hours, is start with the food calories. 375, so make a note of this. This would be number 7. And I see the question over here on the left, on the right side of the room. I'll get to you in a second. So if you do it, work it the other way. Convert the calories to joules or convert the joules to food calories. Either way, you can make your decision. So from food calories to regular calories, multiply by 1,000. And then from from regular calories to joules, multiply by 4.184. Okay. And so then, you get a certain number of joules per trip. And I think the joules per trip is about, the number, yeah, at 1 megajoule. Yeah, 1 point something megajoules. So it's a lot of work doing that. It's astounding how many trips, 185 approximately. So now I don't want to spend too much time on that because for me, doing conversions and stuff is not that important. But we want to do a few of them once in a while, and that's once in a while. Question. What is your name again? Alvaro. mg, the weight force times delta y. Yeah, that's 8467.2. Now there's a question over here on the Sava. The number of joules in 1 calorie is 1 over 4.184. No, wait a minute, I take that back. 1 calorie is 4.184 joules. Okay, so 1 joule is 1 over 4 point, so about 0.2 something calories per joule. Megan. That's the little calories. Question. You convert that, you answer this question. How many thermal calories? And then how many food calories is it? That's these two steps here, number 4 and number 5. Those are the conversion steps. If you choose to work from the food and convert it if you prefer to work from the stadium and convert joules into food calories, this is how you would do it. If you start with 375, you can work the other way. How many, 375 food calories, how many regular calories, okay? And then from regular calories, how many joules? And then you're still going to come up with about 185 trips up the stairs, okay? No matter which way you work it. All right. Now, I mentioned last time the Yellowstone mantle plume. And I didn't have a diagram of it. I wasn't planning to talk about it yesterday. I was planning to talk about it today. Here's a diagram of it. And what this is like a cutaway view or a cross-sectional view of the Earth, the crust and mantle of the Earth below Yellowstone, 2 different slices, one of them going from northwest to southeast, and the other one going from northeast to southwest. And you can see that kind of reddish blob. That's the hot stuff. They colored it red. The reason that they can figure out that it's hot and then color it red is because they use seismographs all around Yellowstone, and there's all kinds of earthquakes happening there all the time. So they have plenty of earthquakes, and if they have like a dozen seismographs stationed strategically around the park, they can figure out by analyzing how fast the signal of a single earthquake gets to each seismograph. They can figure out where the waves are traveling slow and where they're traveling fast. It's kind of like being in a submarine, only you're not listening to sonar under the sea. You're listening to basically sonar under the earth and analyzing it for temperature. So where the waves travel more slowly, that's where the crust or the molten lava is a little bit hotter. And so they can see this. And one thing I want to point out to you is that down here, the bottom of the scale on the vertical left side, vertical scale, that's 800 kilometers below the surface. Up here, here's 0. That's the surface at Yellowstone. So that's where all the grizzly bears and the elk and the tourists and everything else is up there. And then 800 kilometers below, it's about 500 miles down. That's where you can see this mantle plume start. And actually, they could follow it even deeper than that. But for this particular study, they stopped at about 660. And it's kind of cool. And you can see over here, this is a cold area over here to the right side. And here's a different view of that same cold area over here. So it's that's kind of an interesting phenomenon. Now, another thing we talked about was specific heats for different materials. Go ahead and jot this table quickly, if you will. I have some clicker questions about this. And remember, the meaning of specific heat is it is the way that we have chosen to encode how easy it is for a substance to cool off or to heat up, and on the basis of gram for gram. So a single gram of liquid H2O takes 1 calorie for every Kelvin. So the unit of specific heat is calories per gram Kelvin. So I always remember water. If you can remember water, you can figure out the rest of this table. Okay. So water requires 1 calorie, but solid H2O, otherwise known as ice, for your iced tea, only half a calorie for 1 gram to go up by a Kelvin, or as the textbook has it, by 1 Celsius degree. Glass, 0.20. So if you have a gram of glass, it is going to only require 0.2 calories, 0.20 roughly, depending on the glass. There's all kinds of glasses. I'm sure there's probably some that are 0.19 and some that are 0.21, stuff like that. But right around 0.2 for glass, made of sand. Ethanol, liquid ethanol, 0.58. Aluminium, 0.215 calories for every gram. Now here's the thing that you don't really encode here, and that is how many atoms or molecules are in 1 gram. So H2O, a gram of H2O is going to have a certain number of molecules, and aluminum, 1 gram, is going to have a way different number of atoms of aluminum. Gold, look at gold, 0.0301. Copper, 0.0923. Silver, 0.0558. Calories per gram Kelvin. So the heaviest thing on this chart here is gold. So what you're looking at is a gram of gold is a pretty small amount. I mean, volume-wise, because gold is the heaviest of this list of things. So a gram of it's going to be fairly small. Whereas a gram of water is a cubic centimeter. Okay, it's about as big as, like your little finger, the top, above the top knuckle of your little finger is maybe 1 or 2 cubic centimeters. All right, so that's quite a difference. And so gold is going to have fewer atoms. And factored into that is the fact that it's a metal, and all that is smushed together into that number, 0.0301 calories per gram Kelvin. Now, let me ask you an IQ test on the clickers. You ready? Let me start. Which of these substances, same table, we're on frequency BB, which one's harder to heat up gram for gram? How do you read it? of the four choices? Harder to heat up means I got to burn it. I got to turn on my propane burner. You know, I got to go to Hankill, Strickland Propane, and get a lot more propane for this stuff. Propane and propane accessories. $30 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Answer is aluminum. And the and here's the distribution. A lot of you did vote for aluminum. The majority, 71. A bunch of you voted for gold. That is incorrect. The reason that aluminum is the answer to which one is harder, which one needs more propane to raise by a Kelvin, is because its number, its specific heat number right here is the highest of that group. Now there's several things even higher than aluminum. We got liquid water and solid water and ethanol. But of the four options, aluminum, gold, copper, and silver, that's what we got. Now, here's the specific heats in question. So, I don't know, make a star next to aluminum or something like that. All right, let me ask you another question. Opposite question. Which one's easier to heat up? All right, let's see if you guys can put this one together. We know which one's harder to heat up, so don't choose aluminum. It can't both be the hardest and the easiest. It's not a human. It's not the tale of two cities, the best of times and the worst of times. Boy, that's the story of the human race. The best of times and the worst of times. What's that? You know, what I've read of them, yes. I haven't made a program of reading all of it. Have you? I haven't. I hear everybody likes Great Expectations, but I'm such a slacker. Okay, I've been concentrating on Swedish detective mysteries lately, the last year or so. But maybe I should go through Dickens. That's what I do. I get an author and then I just burn through all of them. You know, like over this. Maybe that'll be my summer reading project. Yeah, except the thing is, I read it in English class in high school, so that's like permanently inoculating me against it. Like Shakespeare, Ethan Frome. Ugh. Did you do Ethan Frome in high school? All right, 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys got here. Ding, 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 ding. You got it. Students, you know what this tells me? See how you've frozen out all these other ones almost completely? You're learning. Got you right where I want you. See, I trick you guys into learning stuff. It ain't hard. You think, oh yeah, I got to go to Dr. B's class again. But I got you where I want you. All right. Now, here's an equation that we talked about last time. Let's start again with this. We'll do a little recap. The amount of heat energy, those arrows are pointing in the wrong direction. Ooh, Dr. B. Okay, the one that says how much do you have, that arrow should be pointing at the letter M. That's item 2. The number of grams of it that you've got is encoded in the mass M. And really, what that really does is it encodes as mass, as grams, the number of atoms or molecules that you've got. And because that's the real factor in this. The squiggly arrow is supposed to be pointing at C. What kind of material do you have? Is it gold or is it water? All right, and that's encoded in the specific heat. And then the last thing, you're heating something up. You want to figure out how much Q, how many calories or joules, if you want to work in joules. How many do you need? You have to know how high you're going to raise the temperature. So how much propane do I need? You need to know all 3 of these, okay? And so one of the big factors is how much delta T. Or if you're running a refrigerator, how much do I want to extract? If delta T is negative, that means you're cooling it, and Q would be negative, and so that means how many calories, how many joules do you want to extract? And that's what refrigerators do. Now that's for heating stuff up or cooling stuff down. All right, and we're going to use that in a few minutes. But before we do that, I want to go through the phase transition concepts. We kind of went a little fast over it. Let's slow down and talk about phase transitions. Okay, the solid to liquid phase change, i.e. melting or freezing. To melt something, it takes energy to bust apart, to go in there like Chuck Norris and bust up those crystalline bonds, if it's ice, if it's water ice, and so that it's no longer forming crystals of ice, but still has the ability to form a droplet of liquid water. Okay, that's what melting means. Now for water, it happens at 273. And solid water requires 80 calories per gram to bust up all the intermolecular bonds. They're hydrogen bonds, we call them. They're the ones that form crystals. And if you break them apart, it takes a little bit of work. And there's zillions of them. It takes a very small amount of work, but there's so many of them. On a per gram basis, gram for gram, it takes 80 calories. All right? And make a note that that is at 273. All this stuff happens at the freezing point, melting point temperature. All right? So nothing, as long as you're burning your propane to melt the ice, it's going to stay, if it's still ice, and liquid water and solid water, it's going to stay at 273 until it's all liquid water, and then it'll start increasing its temperature, which we've already talked about. Now, copper. Here's a couple factors for copper and lead in comparison to water. Go ahead and jot this down. Okay. Here's water. We know the factors for it. I forgot to put this over here. Dr. B, napping. Anyways, 273 for the melting point, or freezing point if you want to call it that. 373, 100 Kelvin higher for the vaporization or boiling point. And 80 calories at 273. Now, the thing about water and any kind of a gas is it depends on the temperature. But at sea level, normal atmospheric pressure, there's going to be a number here, and I just forgot to type it in there. I looked it up and stuff. And it's not something that I have memorized. I have 80 and 273 and 373 pretty much memorized, but I don't have anything else here memorized. Anyways, I looked all this stuff up. You can look it up too. I'll show you how to do that in a minute. Copper, the melting point is 1356 Kelvin. And it requires a little bit less calories per gram than H2O. And that is because in 1 gram of copper, there are not as many copper atoms. And also, it's a different kind of a bond. In an in a gram of solid copper, the bonds are called metallic bonds. And those are different from the bonds that make ice crystals of H2O. So the energy, this number here, all you have to do is measure it. I mean, you can predict what it's going to be theoretically, but you still, you make your theoretical prediction, and hopefully it's good, but you still have to measure it. And for copper, it measures out to about 49 calories per gram. Now, I have all the data for copper and lead here, the two metals. And you can look this up for any metal you want, pretty much. I don't know, maybe not uranium, but 2868 is the vaporization point, the boiling point. Whoa, that's pretty hot. That's almost half the temperature of the surface of the SUN, HOT. But, it's a metal, and it needs a little bit of temperature to melt. And then to go from, not to melt, but to boil. And to boil it, every gram of copper needs to go from a liquid state to a gaseous copper state, a gas made of copper atoms, which you can do if you have a good equipment. I'm sure they do it. They probably do it a lot for electronics, because they put a very thin film of metals on your electronics that's perfectly sufficient to conduct electricity. Thin film or very thin layer. And so I'm sure there's a lot of people that make a vapor of copper and other different kinds of metals. Anyways, 868 calories per gram. To make those copper atoms with that much energy per gram, you've turned all those liquid, the atoms of 1 gram of liquid, and you've completely liberated them. They're now just flying around in space like a gas does. And make a side note to yourself, a liquid forms droplets. Why is that? It's not a crystal. It'll flow, but it will form a droplet like water. In that thermal state, they are able to form very weak bonds between the molecules, different from the hydrogen bonds that form crystals of ice, or the metallic bonds that form solid metal. So liquid metal, like a Terminator or like a bubbling cauldron of molten copper, those copper atoms are going to have some interatomic bonding that's very weak, and we call that cohesive forces, cohesion. In other words, they'll cohere into a droplet. They won't form a crystal. They're not cold enough for that, but they'll still hang together a little bit. When they can no longer hang together at all, they become a gas. And they're so hot, they're just zipping around. They can't cohere together. No interatomic forces at all. Now, here's lead down here, and you may ask yourself, what's the deal here with lead? Wow, 5.5 calories per gram to melt this stuff, whoa, that's a low number. Well, don't forget, lead is really heavy, but it's also relatively easy. You can melt it in a campfire. I don't think you can melt copper in a campfire, but lead definitely. That's not that hot for a campfire right here, 600 Kelvin. Okay, so like if you read the old time books, like when I was a little kid in 5th grade and stuff, we'd read about Daniel Boone and Davy Crockett, Kit Carson, and all those guys, and making bullets for their musket. They have to melt lead and all that stuff. And so lead's pretty easy to melt, and but to vaporize it, yeah, it's pretty stout even for lead. All right. And you may be thinking to yourself, hey, Dr. B, where are you looking up all this jazz? Well, one of the really good places to look it up, and if you're not finished with the table, don't sweat it. You can check it out on YouTube. But do make a note of this web address, www.webelements.com. There's a lot of periodic tables on the internets, but this is one of my favorites. This is the one I use a lot. www.webelements.com. So what you do, it's all interactive. So if so here's a little slice of it. If you click on copper, you get a page on copper, and it has all the essentials. And this is just the top of the page. It's filled with great information. So make a note of that website address. And here, for instance, here's copper. Boiling point, melting point, etc., etc. Superconduction temperature, no data. Critical temperature, no data. Liquid range, 1842 Kelvin. Nice. Plus there's advertising in there, but you can ignore that. So definitely make a look at that. Now, I want to show you a strategy diagram for figuring out heat, melt, heat problems. And in fact, heat, melt, boil, and heat again problems. If you want to go all the way to a gas from a solid, this is your strategy page. All right, so let's take a look at this. The vertical scale is temperature, and I have a low starting temperature, so this is like ice down here. And here's my starting temperature down here in the lower left, T subscript I, initial temperature. And then my final temperature is way up here. All right, so there's initial, and heating up means you go upward. Adding heat means you go rightward. So the Q-axis is horizontal. That means to go to the right here, I have to add energy. I got to turn on my propane burner from Strickland propane, right, and burn off some propane. And when I do that, I go to the right. And at certain temperatures, I either melt water right here, or I heat water. I melt ice here, and in this left-hand side, the blue rectangle that says ice water, that's where I'm melting ice. Here's where I'm heating up the water, this red triangle. All right, and then finally I get to my final temperature up here. Now, let's take a look at some of these factors here. The red triangles express the heating up process if you're adding heat. They'd express the cooling off process if you're extracting heat going to the left. But if you're going to the right, we're basically going to do heating up problems and not refrigeration problems. But for going to the right, you're adding so many calories of heat, Q, and that raises the temperature. So it's a triangle. And we don't really interpret the area of this triangle like we did with some of our other triangle graphs. This one we don't really. But it still is nice to kind of understand the strategy of the calculation. Now, right down here, boop, little teeny sliver. of melting my few grams of ice, however many grams. I don't really have it spelled out here how many grams, but you know, this is where they'd be. So this is heating up your ice, this little teeny red sliver triangle on the left, right next to T subscript I. And here's heating up water, this big middle triangle. And then here's heating up steam. And if you are running a nuclear reactor or any kind of a steam engine, you want to make sure that your steam temperature is as high as you can practically make it and keep it, because the higher the temperature, the more work you get out of your engine. Now, the blue triangles encode the process of melting or boiling. So this small blue rectangle that's labeled ice water, in the state of ice water, you have water at the temperature of 273 Kelvin. And if it's in an insulated container, it'll stay, you know, so many grams of solid ice, so many grams of liquid water till the cows come home. If it's in a thermos, there's no external heat trying to heat it up, so it's perfectly happy to stay at that temperature. And chemists use that all the time to keep a constant reference temperature, 0 degrees Celsius, 273 Kelvin, with a thermos and a thermometer. Now, the similar concept holds over here for boiling water. That's a combination of water, liquid water at 373 Kelvin, and gaseous water or steam at 373 Kelvin. All right. Now the difference there is that, and actually it's both things occur. In ice water, the solid ice rises to the top because it's less dense. In boiling water, the gaseous H2O rises to the top because it's less dense. It's steam. It's a gas. All right? It'll convect upward. All right? Now, the general equation for these blue rectangles is simply Q equals mL. Now, M in this equation tells you the mass, and capital L is the number of, that's the latent heat of fusion or the latent heat of vaporization. And so for this blue rectangle, ice water, that equation is used. That'd be the latent heat of fusion, L subscript F. And over here, for boiling water, the latent heat figure that's used there is the latent heat of vaporization, L subscript V. All right. And here are the temperatures kind of listed here. So here's the boiling point temperature. Here's the melting point temperature. Here's the initial one, same as over here, all the way on the left. And then all the way up here at the top, there's T subscript F. All right. Now, we're going to do a red triangle, a blue triangle, and a little bit of a red triangle again to melt a small piece of ice. So let's review this calculation. We did it last time. Let's review it again. And when we're done here, you'll have a clicker question where you calculate the heat budget for a heat process. All right. So we have 10 grams, 0.010 kilograms. Initial temperature 266, and I just decided to make my final temperature 275 just to keep it modest. You know, not too big of a temperature. I could go up to 373 if I wanted to boil it. But let's just go to 275. That warms it up. So this is drinkable. This is cold and nice. Nice, cold ice water. All right? And nothing but ice water. There's no solid ice cubes in this anymore because it's 275. All right, so let's calculate that again. Q1, this is for the heating up of the ice. 10 grams of ice specific heat 0.50 calories per gram Kelvin. And from 266 up to the melting point, 273, delta T is 7 Kelvin. All right, so that's an easy one to calculate in your head. 10 times 0.5 is 5. 5 times 7 is 35. So that's 35 calories. And notice here, you guys, I didn't animate this to show you the cancellation, but you can do it in your notes. Grams here cancels grams in the denominator of the specific heat. Kelvin in the delta T parentheses cancels Kelvin in the denominator of the specific heat. So all you're left with is good old calories, which is how it's supposed to work. So that one works out to 35. Now, heating up the liquid water from melting point 273 Kelvin up another couple kelvins to 275. We have 10 grams still. We haven't lost any. All right. And if you were a scientist studying icebergs in the Arctic, you might want to know about evaporation and stuff like that, solar radiation. But for us, we'll keep it simple. So we're going to say that there's 10 grams of liquid water. Specific heat, 1.00 calories per gram Kelvin. And this one, I'm going from my melting point temperature, Alexis, up to my final 275. So I just have 2 kelvins. Do you have a question? Alexis is asking me, why are there 2 different delta T's? And the reason is we're doing 2 different red triangles. Okay? And that depends on what your final and your initial temperatures are relative to your phase transition temperature, 273 in this case. All right? Now, the change of phase, as we said last time, just take 80 calories times however many grams you have. All right? And so for us, that's 800. 800 calories per gram, latent heat, 80 calories per gram, latent heat of fusion for H2O. For 10 grams, that means you got 800 calories. Now you're going to have to write that one in. 10 grams times 80 calories per gram is equal to Q, and so that'd be Q3. The third Q that you, and you don't have to do them in this order. You can do them in any order you want. Alexis, you still have another question? Melting point. Right. Because one of them is, Alexis is asking me, how come I'm going from 0.5 here to 1 down here for this specific heat? 2 different substances. I've melted, this is ice, I've melted it, this is now liquid, different specific heats. Okay? So liquid water, it's 1.0, solid water, 0.50. You need it for both phases, and that's the, so you got to balance a lot of information. Right? Anyways, your total heat budget is 35 plus 800 plus 20. So that makes a total of 855 calories for this task. Let me pause for a question. Gabby. 800 is right here. It comes from the melting. These, and I always call these heat melt heat. Okay? The melting is on a gram for gram basis. So you need 80 calories of energy to melt a gram of solid ice at 273 and turn it into liquid water at 273. Now we've got 10 grams of it, so that means 10 times 80, 800. All right? And so you've got, so these Q1 and Q2 Go ahead and make a note of it. Q1 and Q2 are two different red triangles. On Gabby, on that previous diagram, okay? And this one, number 2, the change of phase, that's a blue rectangle, all right? And so that strategy diagram that we just did, you could actually do another version of it with the exact numbers and everything, you know? And it would just have 2 triangles and a rectangle between them. Alexis. What is the exact information used for C? It is the information in the table of specific heats that you were given at the beginning of class and that you will be given on the cover page of exam 3 if you need it. And so it's just, in other words, it's something you look up. I have to look them up every time. And so I'll give you guys a table in the exam. You won't have to worry about, digging it out. All right, let's try an example. Let's melt some heat. Let's melt some ice and heat it up. And when you're doing this, hit the refresh key on your calculator, by the way, or your clicker. And just work with it. Can you turn the lights to full? Here's your question. And let me start it. This is a calculation. And let's start it. Okay, so take your time and let's do this carefully. Yeah. See what you can do. Turn off the left. Is that better? I mean, this projector is pretty bad. Just go back to presentation. Yeah. You guys are both on your computers, so all right. Yeah, I guess they have enough light. You have a 120-gram chunk of ice up in Greenland. Initial temperature is 260. So 260 up to 273, there's your first delta T. You want to warm it up to 300. So 273 up to 300, that's another delta T. Slightly different. And you got to melt it. 120 grams, 80 calories per gram. And if you do that, you can have a cup of tea. And you can give this polar bear a little wake-up cup of tea. Yeah, but it's obviously summertime, so he doesn't have to cool off. He's, and plus it's morning, in the land of the midnight sun, it's the middle of the night for him. So he's taking a nap. And I could tell from personal experience, you need a cup of tea when you get up, or a cup of coffee. Alvaro. George, you got it? Carl, you got it? All right. And students, traditionally, this is one of the major brain burners of the semester. Either of these two TAs of mine or Shy, the three of them can all attest that. $80 times, let's see, 120 let's see, 300 Kelvin, 120 grams, specific heat, great expectations. Let's see, I've read of Dickens, I've read Tale of Two Cities and Christmas Carol. That's it. Yeah.
Really? I mean, it's the shortest one.
Yeah, it's pretty short. It's actually kind of ferocious. It's frightening, really. It's very very grim. Yeah, I've never read that. I've heard, and there's a three of those through the looking.
Yeah, through the looking glass.
Really? Yeah. You know, The Wizard of Oz,
Oh yeah.
the L. Frank Baum, he wrote a bunch of
There's
books.
like 6 or 7.
Yeah, and I remember, like, since first or second grade, my teacher read a couple of them to us and stuff. You know, during our, how in first grade you take little naps and stuff in class. Yeah. Whereas in college you take naps during class, anyways. A lot of people. Where's Miss Brittany? She's been missing a lot of class.
I mean, she can get more than you can on.
I know, but I mean, is she okay?
I think she's probably just
Oh, a student? Busy?
well, she's a double major.
She is? What's her double major?
Communication and I think psychology.
Oh, they're way different, so there's no overlap. So that means double amount of work.
So
Yeah.
she's.
Buried.
I'm not 100% sure. I know one is music education.
Yeah.
Music education is a lot. I mean, like that's the most credits you need for.
Really? Yeah, that's good. Good gravy. These guys are burning up the charts here. Yeah, look at that. 1 minute. $30. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see you guys got here. Oh my goodness. Raise your hand if you got 13,620. Sweet. Geniuses. See now, you guys, I think this is the fastest I've ever gotten to 80%. These guys, you know what else? I forgot to say something to you a couple weeks ago, and I want your full attention, if you please. You guys have done an awful lot of work I mean, maybe you don't feel like that, but I've really pushed you pretty hard. And you're doing really well. I'm very happy about it. And I think you should. I'm going to give you a hand. And you can give everybody else a hand if you want. I'm I'm very I'm very happy with almost everybody, uh, except for a few people that hardly ever that I'm not looking at that don't come to class all the time, maybe. But anyway, I'm very happy. Another clicker question. And hit your refresh key because this one's multiple choice. So a total of 3. Total of 3. Yeah, so 3, right? Right, 2 to the third power is 8. Do not let me toss you for a loop like that. Do not, Alvaro, do not let me catch you napping. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Uh-oh. We got some splaining to do. A bunch of you voted for 3. No, that's no good. There's only 2 phase transitions. Do not. Shh. Students. Do not let me toss you like a rag doll. I was messing with these guys up here, and I was trying to see if I could throw them for a loop, and it looks like I threw a bunch of you for a loop. Now here's how you work your way through it. You start it. You got to know your phase transition temperatures. For water, it's fairly easy. 273 and 373. That's the only 2 you got. All right? So at each temperature, you have a phase transition. First one, from solid to liquid at 273. Second, from liquid to gaseous at 373. Now, for those of you that typed in 2, you're correct. Those of you that typed in 3, you might have been thinking 3 phases, solid, liquid, and gaseous. There's only 2 phase transitions. Question? Oh! Oh! Dr. B, I completely misread this chart. You're right. This doesn't look. Raise your hand if you typed in B. How did it come out this way? This is strange. Because, shh, look at this. You know, I've been getting some flaky things from this software lately. This is, all right, I'll give everybody points on that one. Let's try another one. Now, see, this is a way of going step by step through heat, melt, heat, boil, heat. This is one of the questions that you have to ask and answer correctly. Twenty seconds. Five, four, three, two, one. And I kind of goofed that up, but I don't think everybody changed their answer. We, we got a lot of correct answers there. That's good. Now, let's get back to regular notes. I have a few more comments about attaining the gas phase. Question?
Yeah, I got to eat, but I didn't know how to get from the liquid state to the gas state. Like what temperature?
373 always. Water. Yeah, always. All right. Gas phase. I have some fine points about this that I want to go through with you. Then a liquid can go to a solid by freezing or to a gas by boiling. Now, we've already talked about that. A solid can go to a liquid by melting, 2B. 2A, a solid can actually go to a gaseous state, and that is something that we call sublimation. Sublimation. And a good example of that is dry ice. Dry ice goes from a solid CO2, really cold, at atmospheric pressure at sea level and so forth, straight to a gas. It doesn't go to a liquid. All right. A gaseous substance can go from liquid by, and that's what we call condensation. So like rain goes from water vapor to liquid, forms little mini micro droplets and eventually a big enough droplet to fall out of the sky. Or it could go straight to a solid. And that's what a lot of electronics techniques use to manufacture an electronic chip. They use something called epitaxy or deposition, vapor deposition. And what I want to talk about is a couple things here. The gaseous is usually considered higher energy and solid is usually considered lower energy. But the pressure of your container or the pressure of your environment in your lab does have an effect. Here's an excellent example that you may have heard about. If we lived out in Colorado, you up in the mountains, you would have lived with this for many years. If you try to bake something at high altitude, you have to change the recipe and change the heat, the temperature that you bake at, because the altitude makes a difference in how fast the chemical reactions proceed. And so if you look at, if they probably don't sell it down here in Florida with instructions like this, but if you're out west in Colorado or Montana, you'll see on the back of a box of pancake mix or cake mix, high altitude instructions. Okay, and it's significant. And that's because the air pressure, the higher up you go, the lower the air pressure is. And so the ambient pressure affects phase transitions. And here's a good example of that. This is dry ice. And dry ice, here in Orlando, you buy some at Publix, a big block of it, and it'll go straight to gas. They call it dry ice because it melts. It doesn't melt. It goes straight to a gas. You know what will happen is it will, if you put it in an enclosed container, which I did one time, it'll cause the enclosed container to explode. One time I was fooling around with CO2, dry ice, in my garage, and I was dropping little chunks of it into some vinegar, into a water bottle that had like an inch of vinegar at the bottom, just to see. I got a guy up here in the second row going, Dr. B, why'd you do that? Just to see what would happen, because I wanted to do a demonstration in class. So I was doing this, and then I was doing water and see what would happen if you drop it in water. So anyways, so then I thought, oh, this stuff's not cold enough. So I I filled up one of these little basins, like the basin where you soak your feet at night, with Epsom salts and stuff. And I just filled it with regular hot water from the tap. And I put it out in the driveway out in front of my garage. And then I put it into one of these little, like a little water bottle you buy, disposable water bottle. I put some water in there and a couple chips of dry ice. And then I screwed the lid on and I put it in the hot water. And all of a sudden, bam, there's this big explosion. And my wife came charging out, are you okay? And I was in the garage, so I was all right. But that basin, the bottom of that water bottle blew a circular hole in the side of that basin, perfectly circular, like it wasn't even there, like a pair of scissors. All right, we'll talk about dry ice again on Tuesday. You're dismissed. Good class today. It was unbelievable. All right.